Hello, today we're going to talk about the equilibrium reactions of weak acids and weak bases. Okay, so let's talk about weak acids first. In general, we'll use HA to represent a weak acid, A for acid, but you should know that A is, whatever that ion is that makes it a weak acid and not one of those 7 strong acids. So don't ever on your AP test, don't ever write in HA unless it specifically tells you to use that thing. It should be whatever that substance really is. But your weak acid will be in a water solution. So in water, this will act as the acid, the water will act as the base, and so the acid will lose a hydrogen and transfer it to the water. Now because it's weak, it only partially does this. So you wind up with A minus plus H3O plus, like this. So this is your conjugate acid and conjugate base. Now, water is a liquid here. Your weak acids and weak bases will always be aqueous. And then, of course, your ions are aqueous as well. Okay. So that's kind of the general equation, but you can apply that to whatever weak acid you're dealing with in any given situation. Now, again, because it only partially ionizes, it only partially does this, we can write a equilibrium expression for that. And we call it Ka, A for acid. And it's always products over reactants. Products over reactants. And we don't include the water because it's a liquid. Now, a lot of people will just use H plus here instead of the hydronium. You can use them kind of interchangeably. For right now, I'll use the H3O plus version. Okay. So that's your Ka expression. And remember, it's products over reactants. So if you have more of the ions, your Ka value will be larger. So that means if your acid breaks down into ions more, you will have a larger value of Ka. So the stronger the acid, the more it breaks up into ions, the larger the Ka value. Okay. So you can very easily compare Ka values between acids and see which one is the stronger acid, because it will break down into more ions. Now, because this is an equilibrium, we can always use an ice chart to figure out how much of something that we have. So I'm going to just rewrite my reaction really quick. HA plus H2O. It's actually pretty similar to KSP in that you assume that if you just have a weak acid solution, you assume you're putting the acid into water, and your initial is the instant that you put it into water, so it hasn't broken up into any ions yet. And so when you're doing that ice chart, you don't have any ions yet, and the water doesn't matter because it's a liquid. You just have your concentration of your acid, whatever that is. I'm going to use C. Let's use C for concentration. And then some of that HA will dissociate into ions, so some of that will break down, and it will form some products. So the products will increase, the reactants will decrease, and it will follow the stoichiometry. So if it's not all 1-to-1, please make sure that you update the coefficient of your X, just like it is in the balanced equation. So whatever your concentration is, minus X, your A negative will be X, and your H2O plus will be X. So X is equal to your H2O plus. This is important. Okay, if you can find X, then you can find the pH, because pH is equal to the negative log of H3O plus, or just H plus. So if you take the negative log of X, you get the pH, which is a very frequent question that they ask. So we can do a very similar thing for weak bases. We're going to use B for a general weak base, but make sure you replace it with whatever the base actually happens to be. And it's a weak base, it's aqueous, it's going to react with water in the solution, and it's weak, so it's going to form an equilibrium. And so the hydrogen will transfer from the water to the base. This is our base. The water must be acting as an acid here. And so you'll wind up with H being negative. And this is our conjugate acid. and you'll be left with some hydroxide ions left over from the water, and that's your conjugate base. And those are aqueous as well. And from here, then, we can write our Kb expression. Products over reactants, so Hb negative, it's our conjugate acid times the hydroxide ions, all over the concentration of the base. We don't include water because it's a liquid. And so this is our Kb expression, B for base. Just remember to replace B with whatever the substance actually happens to be. Oh, this should be Hb plus, I'm sorry. I wrote that wrong. Okay. And of course you can use an ice chart to solve for these as well. So if I have my base plus water, Hb plus, OH negative. Okay. And again, just like we were doing with the acids, you assume that if you just have a solution of that weak base, okay, you're not doing any other reactions or anything, you assume that the initial conditions for our ice chart, so you don't have any ions yet, it's the instant you add the weak base into the water, and then we didn't include the water because it's a liquid, so whatever the concentration of that weak base is, the products will have to increase because you're starting at 0, reactants will decrease, and then you need to follow the stoichiometry of the reaction, so you'll get C minus X, X, X. Now you can plug those values back into your Kb expression, depending on what they give you, and then if you are able to solve for X, that's great because it's equal to your hydroxide ion concentration. So then if you take the negative log of X, you get the POH, which is great, because from POH you can really easily find the pH of the solution. So that's how we need to solve weak acid and weak base equilibrium. Okay, we need to talk for just a minute about pKa, pKb, and Kw. So if you remember, at 25 degrees Celsius, Kw is equal to 1 times 10 to the negative 14, and that the expression is always, the H3O plus times the OH negative. Okay, just like that. And you can replace H3O plus with H plus if you choose. I'm going to stick with hydronium for this one. All right. Now remember that lowercase p means negative log. So you can find what's called the pKw, which is the negative log of Kw, which is 14. Okay. You can also find what we call pKa, which is the negative log of the Ka for a weak acid, and pKb, which is the negative log of the Kb value, which we're talking about for weak bases. So now if you have two things that are conjugates of each other, then you can do pKa plus pKb equals pKw, or you can simplify that to just 14 because it's almost always at 25 degrees Celsius. So that's really helpful, but it only works when they're conjugates. So what that means is, like, if your acid is, let's do NH4 plus is your acid, and your base is NH3. You would need to use the Ka value for NH4 plus. And then you can solve for the pKa and find the pKb and go backwards to get the Kb for your NH3, or vice versa. But it has to be for conjugate pairs. They have one hydrogen difference and one charge difference. So that's kind of how we can go back and forth between them. Let me think of another example. Oh, if you have the weak acid, acetic acid, it's a really common one, HC2H3O2, acetic acid. Its conjugate base is C2H3O2 minus. But again, you can convert between the pKa of this weak acid and the Kb of its conjugate using these equations here. Let me just make a little side note about acetic acid since we're here. Sometimes people will write acetic acid as CH3COOH, and that just has to do with the actual structure of acetic acid. Acetic acid looks like this, where you have a CH3, like C with 3 H's attached to C, double bond O, OH. And this hydrogen is the acidic hydrogen. That means it can leave and be donated to the solution. So it's the acidic hydrogen. So that's why sometimes you'll see it written like this. And so its conjugate base would be written CH3COO minus, like that, because it's the hydrogen at the end that gets taken off when it does an acid-base reaction. I don't typically like to use that notation because it's more of an organic chemistry notation, and it's not, it's a little bit beyond the scope of AP chemistry. I like this notation better, but you should still kind of recognize the other notation just in case they use it in an example or something. Okay, so let's talk about percent ionization. Let's go back to our generic weak acid. Or actually, let's use a common weak acid, HF. So HF, when it reacts with water, it will form F minus is our conjugate base, and it will form H3O plus is our conjugate acid. Okay, so if you were to write your Ka expression for that weak acid, you would get F minus times H3O plus times the original concentration of HF, and we don't include the water, right? Now let's think about what happens when you put HF in water, and the instant you put it in, initially, you have some concentration of HF, we don't include the water, and we have 0 fluoride and 0 hydronium. The concentration of the HF is going to decrease by X. The F negative will increase by X, and the hydronium will increase by X. So you wind up with C minus X, X, and X. Now, so this is basically telling us how much does the original one go down, and how much of the ions did I form. To find percent ionization, okay, you're going to use this X value, because it tells us how much is now ions, over the original concentration times 100. So the amount that wound up in ions over the original concentration times 100. And we'll always make a fraction because it's a weak acid, so you'll only ionize some of it. So it will always be less than 100%. And you can figure out the specific percent that actually broke down using this simple equation. Okay, so we have the pKa of hypochlorous acid is 7.54. What is the pH of a 0.1 molar solution of HClO? All right. So this time they gave us pKa, which is interesting, but they're perfectly able to do that. Remember, pKa is just the negative log of the Ka. So we can solve for the Ka by plugging in the pKa here, 7.54, and doing 10 to the negative 7.54 to get our Ka. And we get that Ka is equal to 2.9 times 10 to the negative 8. Okay, I'm going to save that. We're going to need it. Now, our hypochlorous acid will react with water to form ClO negative is our conjugate base, and H3O plus is our conjugate acid. And so if we make our ice table, water doesn't count because it's a liquid. We don't have any of the ions to begin with, but we have a 0.100 molar solution of the hypochlorous acid to begin with. This will decrease by X, increase by X, increase by X, so 0.100 minus X, X, X. Let's go ahead and write our Ka expression. It's the ClO negative times the H3O plus all over the HClO. And we always plug in equilibrium values, so you'll plug in, we have the X, X, and the 0.100 minus X. And we found our Ka value was 2.9 times 10 to the negative 8. So now you can solve for X. I suggest using a graphing calculator so you can make this a lot quicker. 2.9 times 10 to the negative 8 times 0.100 minus X equals X squared, and you'll get that X is equal to 5.4 times 10 to the negative 5. Now, that's X. So X is equal to your hydronium ion concentration, and that's useful because it's asking about the pH. So to get from X to pH, we need to just take the negative log of the 5.4 times 10 to the negative 5, and you'll get that the pH is equal to 4.27. Definitely acidic still, which makes sense because it's a weak acid. So yeah, there you go. Here's another example, but this time with percent ionization. Calculate the percent ionization for a 0.155 molar solution of acetic acid, and the Ka is 1.76 times 10 to the negative 5. Acetic acid, which we talked about. Let's go ahead, plus water. Our conjugate base, hydronium. Okay, water doesn't count because it's a liquid. And our original concentration is 0.155, and we don't have any of our ions. The acetic acid will decrease by X, the acetate will increase by X, and the hydronium will increase by X. So 0.155 minus X, X, X. Let's write our Ka expression. The acetate, C2H3O2, times the hydronium all over the original acetic acid. And our Ka value is 1.76 times 10 to the negative 5. We have X, X, and 0.155 minus X. I suggest using a graphing calculator to solve for X, and you get that X is equal to 0.00164 molar. And so since that is the concentration of our ions, and it's asking for the percent ionization, we can take the 0.00164 and divide by my original concentration times 100. And you'll get that the percent is 1.06% ionized, which is small, but that makes sense because it's a weak acid, so only some of it dissociates. And specifically 1.06% of it dissociates into ions.